So the topic of today's lecture is motion in central potentials. And later we're going to come to the three-body problem, or the restricted three-body problem. As you might know, the three-body problem can't be analytically solved, so we're going to have to be satisfied with a restricted three-body problem. So as I said, what we're going to talk about today is motion in central potentials. So what is a central potential? Well, a central potential is that we consider a potential, and in general our potentials have depended on position x, but in this case we're going to say that this potential only depends on the distance r from the origin. So for example, the Kepler potential of gravitation, which is a 1/r potential, or a harmonic potential. And we're going to discuss those later. So for example, if you have your sun here and you have the earth going around, it's essentially moving in a central potential where the distance r is the distance from, well, in reality the center of mass of the system, but which is essentially the position of the sun. And the full Lagrangian of this system in 3 dimensions, or in general any dimensions, is going to be that the Lagrangian is equal to, well, the kinetic term, which is m x dot squared half, minus this potential v of r. And this we are already used to. Now, since this Lagrangian does not depend on time, we have time translation symmetry. So this tells us that, that this Hamiltonian, which is going to be equal to m x dot squared over 2 plus v of r, as we call it, and that's going to be a motion. All right. But this potential, since it's only a function of r, has some additional symmetry, and that symmetry is rotational symmetry. So we can rotate this potential around this center, and we regain the same system. And in general, a symmetry, as we discussed by Noether's theorem, means that we're going to have a constant of motion, which we call J, which is equal to the L, the x dot, and scalar product with the infinitesimal generator of the symmetry. And in this case, this is going to be equal to m x dot, so the physical momentum, times delta x. Now, for rotation, around some axis omega, this is equal to omega cross x. So this is the generator of a rotational symmetry. So inserting this means that our constant of motion, which I'm going to call L for reasons that will soon become apparent, is going to be equal to m x dot inner product with omega cross x. And this is a triple product, so we can make a cyclic permutation of this without changing the value. So I'm going to pull out the omega, and we get x cross mx dot. And now, since this omega is arbitrary because we have rotational symmetry about any axis, this thing here, the x cross mx dot must also be a constant, must be a constant vector. So I'm going to call it L vector, which is x cross mx dot, is a constant of motion. And of course, you recognize this if I just write that this is the physical momentum p. This is x cross p, so this L here is the angular momentum. Okay, and so due to our rotational symmetry, this angular momentum is conserved. Any questions so far?
Yes, I have a question. You've written that L is equal, at the beginning of the line, you've written that L is equal to this mx dot and so on. I assume that you mean the Lagrangian?
No, this is just my constant of motion. Sorry.
Yeah.
I mean, typically a Lagrangian I write with this curly L.
Yeah.
Whereas this is just
I was a bit
straight
confused.
Yeah.
It's just that. Thank you.
Okay. So already we can see, just from this, we can deduce something interesting, and that's that since this vector is a constant of motion, and it's a cross product between two vectors, one vector which is the position vector, and then we have a constant which we can essentially forget about for this purpose. We can divide out the constant, and then this velocity. This means that both the position and the velocity must be orthogonal to L. And so this means that since L is conserved, that both x, the position, and the velocity x dot must be in a plane perpendicular to L. So that means that we can actually make some simplification here. So we know that x and x dot are restricted to a plane which is perpendicular to L. And so I can choose my coordinate system such that I use polar coordinates in this plane. And in that case, I'm going to be left with a Lagrangian that looks like this. So I have L, and then I have the usual polar coordinates here. So r dot squared plus r squared phi dot squared, and minus the potential V of r. So now I have gone from what was a three-dimensional system to a two-dimensional system, because due to the constant of motion, I could deduce that the motion was actually in a two-dimensional plane. And that's pretty neat. So what we discussed last time was effective potentials. And in particular, in this case, we can see that we have exactly the kind of case that we were discussing. So this Lagrangian that we have here is only dependent on phi dot. It's not dependent on phi. So our Lagrangian is explicitly independent of, it's not explicitly dependent on phi, which means that we have a constant of motion which is exactly the same as the absolute value of this vector. So that is going to be L m r squared phi dot in these coordinates. So using this constant of motion, we can rewrite, exactly as we did last time, we can rewrite this problem as an effective problem in R only. So our effective Lagrangian in the R coordinate is going to be L effective. I'm going to have m r dot squared over 2 as the kinetic term. And then we're going to have minus V of r plus L squared divided by 2m r squared. So this here is the effective potential. Which we call V effective. And just to see how that looks like, let me draw a bit. So, oops. So if we have V effective or V in general on the vertical axis and R on the horizontal axis, if I now draw whatever kind of potential I had from the beginning, this is V of R, and I draw this additional term that we got from the angular momentum. So this is called the angular momentum barrier. That's going to be a 1 over r squared, and it's positive. So it's going to look something like this. So this is the angular momentum barrier again. It's proportional to 1 over r squared. So I also mentioned last time that this angular momentum barrier, it's called this because in general.
I'm sorry, your mic cut off.
General from going to r equal to 0, and the only it's going crazy.
Yeah, your mic cut off in the middle of the sentence.
Yeah, I'm going to try to check the connections on this guy.
Now I can hear you, but yeah.
Yeah. So just interrupt me again if it happens again. So what I said was that this angular momentum barrier generally will stop you from reaching r equal to 0, because the effective potential in total is going to be the superposition of those two. So something like, well, something like that. So this is V effective. And so if you have an energy like here, you will always have a point like there, which you cannot pass. You cannot go lower in R. This of course always happens as long as your original potential does not diverge faster than 1 over r squared. If it diverges, if it goes to 0 faster than 1 over r squared, then you will be able to reach r equals to 0. But we don't have many such potentials in nature. Now, one interesting thing is to note that if you consider just gravitational theory, you know that you have a 1 over r potential. This is called the Kepler potential. This is only true in 3 dimensions. If you go to 4 dimensions, for example, you instead will have a 1 over r squared potential, which would generally mean that either you're going to reach r equal to 0, or you're going to go off to infinity. And those are your 2 options. So in D equals in 4 dimensions, you don't have stable orbits in the gravitational potential. And also for r equal to 2, for D equal to 2, when you have a logarithmic potential, well, that potential grows as you go to infinity, and it also diverges slower than the angular momentum barrier. So that results in all of your potentials being bound. It's also kind of interesting. So actually 3 dimensions is the only case where you have both bound and orbits and orbits that diverge. Of course, you can always reach r equal to 0 if your angular momentum is 0, because then you don't have this angular momentum barrier. So the question is, I mean, we discussed L, the angular momentum. So what kind of, oops, I do not want to be blue. What, I also should learn to spell. What kind of conclusion can we draw from L being constant? And you might be familiar with this. So if we look at how L is defined, I mean, the angular momentum with a vector, it was defined as x cross m mx dot. So if I just divide away m, so L bar over m is, let me divide it by 2 as well. 1 over 2 x cross x dot. Okay, so what does this mean? Well, if I have my vector x like this, and I have x dot there, and let's do that. So what is the cross product of these two? Or rather, what is the geometrical interpretation of the cross product? Well, that's going to be the absolute value of this. So if I just do that, if I take the absolute value here of both sides, the absolute value of the cross product is the area spanned by these two vectors. So in essence, if I take, oops, if I take these two, and I do this, oops, this area here that I have spanned, that's the absolute value of the cross product between x and x dot. And if I divide that in half, so I can do that by drawing this line, what I'm left with is this area here. And that area, so if I go time dt, this area is the area swept from this point to that point, right? So this is the area swept in a time dt.
I'm sorry, from what point to what point?
It's the area, if I draw the triangle, right? So, well, in general, if I have the center point here, and I go from here to here, it's going to be the area swept by this object moving from here to here.
Ah, yes.
This is the area, right? So this expression here is the area swept per time unit, because the x dot is the displacement per time unit. So this means that this area is constant, right? This area swept per time is constant because L is constant and M is constant and 2 is constant. So this is Kepler's second law. Which just tells you that the area swept per time unit is going to be constant. So this is actually not only true for the Kepler potential, but it's true for any central potential. It's just a consequence of conservation of angular momentum. Any questions on that? Okay, so let's just discuss a few examples of central potentials that we're going to look at later as well. So the first example is a harmonic potential. So this is just a potential V that is proportional to r squared. So it's now some k half times r squared. So this would be, for example, where you have a force that is linearly proportional to the distance that you are from the center. And in this case, if we look at this diagram we drew before, so if we put V on the y-axis and r on the x-axis, we still have this angular momentum barrier, which looks like this, and we have the r squared potential itself, looks like that, and it goes off to infinity there. The angular momentum barrier goes off to infinity there. So this means that that if you look at the effective potential, it's going to look something like this, going off to infinity at both ends, which means that regardless of what your energy is, you're always going to be left with some classical turning points. So in the harmonic potential, you only have bound orbits. The second example is a Kepler potential. So in the Kepler potential, instead of having this r square potential of the harmonic one, you have, this is minus some constant divided by r. Now, if we go to gravity, K is g m, where g is Newton's gravitational constant, and capital and small m are the masses of the two objects. And in the case of the Kepler potential, as we discussed in 3 dimensions, we have the following situation, that, well, the angular momentum barrier, we'll draw it something like this instead. That looks something like this, while the 1 over r potential is going to look something like this. So what's happening is that since this is 1 over r squared, or proportional to 1 over r squared, and the potential itself is proportional to 1 over r, for small values of r, the angular momentum barrier is going to dominate. So we're going to go off here. However, for large values of r, the Kepler potential is going to dominate. So we're going to follow the Kepler potential pretty close, not below it, but pretty close, which means that we're going to have negative values for large r, which means that at some point we have to cross here and go up like this. Oops. Let me try to draw that more or less fine. So something like this. And that means that we have 2 types of solutions to this. If the energy is above 0, so if we're up here, since that is larger than the value of the potential as r goes to infinity, there is no upper classical turning point, there is just this lower one. That means that those orbits are eventually going to end up at infinity. Whereas if the energy is smaller, then we're going to be down here, and we are going to have 2 classical turning points, and that's going to correspond to bound orbits. So in this case, we have both bound orbits and free free solutions to this problem, depending on the value of E. Any questions on that?
So the physical interpretation of that would be, if you have a satellite orbiting the Earth and you give it a high enough kinetic energy, it's gonna leave the the orbit around the Earth, and it's just
I mean, if you give it enough energy to have a velocity which is higher than the escape velocity, then it's going to fly off.
But is that represented in this diagram?
That is represented by this in this diagram, because here is just potential energy, right? But so if the total energy is larger than 0, which is essentially to say that that the kinetic energy is larger than the binding energy, then you're going to go off to infinity because there is simply no way of stopping you. Whereas this cannot happen in this case of the harmonic potential because there is no binding energy, so to say.
I wonder what's the difference in, or can you hear me?
Yeah, I can hear you.
What's the difference in looking at the normal potential 1/r and the effective potential?
So with the effective potential, we are describing the entire problem just by looking at one coordinate, looking at r. If you look at just the potential itself, then you also need to take into account how you move in the phi direction. So what we have done when we go to a description that is just involving the r coordinate is that we have used the fact that the angular momentum is a constant of motion to transform our problem to a one-dimensional problem. And we can see how the solution behaves looking at this effective potential.
Okay.
Okay, so I mean, those are two examples of central potentials that come in quite handy at times. And you can also see here exactly what I said, that if I would instead here put a 1/r square, it would depend on the constant I put in front, but either the potential would go off to -infinity or +infinity, or it would just be flat. So in that case, you would either go that way or that way. There would be no stable orbit like these orbits here, which go between two classical turning points.
I wonder about the minimum there on the blue graph.
This minimum.
Yeah.
Yes.
Does that mean that you're? Oh yeah, that's. Does that mean that you're moving in a circular?
Yeah, exactly. So I mean, as you go towards this minimum, if I draw this guy, these classical turning points are here, right? I go to these points, the classical turning points, they kind of get closer and closer, and eventually they merge there, right? And this means that since if I draw that energy line, so let's do this and then we move it. Otherwise, it's impossible to draw it correctly. So if I have this energy, right? I have two classical turning points. I have a turning point here and I have a turning point there. And as I move down, those turning points they go towards each other, and eventually I'm there, where I only have one point, which is where you can be. You cannot be in any other points because that would violate the energy conservation. So this turning point, or sorry, this minimum is exactly what you said. It's when you get a circular orbit, because the only radius where you can be with this energy is this constant radius. So the only solution is that r dot is 0, leading to r being a constant. That is correct. Okay, so another thing that I wanted to discuss is what's called orbital precession. So in general, for a general central potential, I mean, you might know that solutions to the harmonic potential and solutions to the Kepler potential happen to be ellipses, and we're going to see that happening later on as well. But in general, if you have a central potential, there is a priori no reason why the period in the angular direction should be the same as the period of oscillations for the radial direction. So let's just check that. And we are going to consider orbits close to close to this, exactly what you said, close to this orbit where we have circular orbits. So I'm going to call this point R0. So let us consider orbits close to the circular orbit. So I can write rho equal to r minus r0, where r0 is this position of the circular orbit. And then we can ask the question, what is the angular difference in phi between consecutive minima for r or rho? Of course, since they differ by constant, their minima will occur at the same points. And we already know, because we discussed this last time, what is the period of oscillations in the rho direction. So this is going to be this entire framework of making this integration. So that's going to be 2 pi, and then the square root of m divided by the second derivative of the effective potential at R0. So this is the period in rho. Or equivalently the period in the r coordinates. And it's an approximation because we are close to a circular solution. So what remains to see if that period, or how that period compares to the period in the angle phi, we can look at the angular momentum again. So L over m, that's approximately equal again if we are close to a circular orbit. R0 squared times the phi dt. And that's just by definition of the angular momentum. And so I can integrate this. If I integrate this over a period in rho, I'm going to get how far it is between consecutive minima in phi. So the phi dt, I integrate that from 0 to t rho with respect to t. And this is going to give me the change in the angle between consecutive minima. So this is approximately equal to L divided by m R0 squared. And then I get 0 to t rho dt, and this of course just evaluates to t rho. This is L t rho divided by m R0 squared. And if I insert my expression for t rho from before, so this expression, we end up with 2 pi L divided by m R0 to the fourth, the second derivative of the effective potential at R0, and the square root of that. So the question now is, when do our orbits close? And the orbits close if this thing is a multiple of 2 pi. No, sorry, if this is a 2 pi divided by an integer, then your orbits close. So this means that this entire thing, the square root of m R0 to the fourth V effective double prime at R0 divided by L. That is an integer. Then orbits close. Or rather, they close at least to the level that we have computed, because we had some approximations here. We had this approximation and we had this approximation. But if this is not an integer, then the orbits will definitely not close, even to first order.
What do you mean when you say that they close?
So the angular distance between two consecutive minima is such that on consecutive laps, you're going to come back to the same point.
Okay.
So if I draw that, if I have my center here, and I start here. So however I move, I mean, it's not going to look like that, but I come back to the same point.
Okay.
With the same velocity. Now you might know that for the Kepler potential, this is an ellipse. I'm going to show that shortly. And the ellipse closes. It actually closes exactly, not just to leading order as we looked at here. So that the opposite thing, of course, would be that it doesn't close. So let me draw that as well. So that it doesn't close would look something like this. So if you start out here and you go around and you come back to there and it goes something like this. So in consecutive laps, you're not at all at the same point, but you have a precession of, oh, well, the minimum or the maximum distance. And I mean, you might be aware that this was one of the first hints for general relativity, that even taking, I mean, the solar system has many bodies in it, so it's not really just a central potential, but even taking those into account, if you look at the actual precession of the orbit of Mercury, Newtonian physics was not able to explain the full precession. And so that was a mystery that was resolved first when general relativity was introduced. And before that, there was all kinds of different speculations that maybe there was a 10th planet called Vulcan, much closer to the sun, which would affect Mercury's orbit, or something like that.
Did Mercury orbit in was it expected to orbit in a non-closed orbit, or?
No, I mean, if you just look at the central potential, it's not. It's just expected to go around in an ellipse. Mm-hmm. However, in the solar system, you have other bodies than the sun affecting the orbit. For example, right. Jupiter is going to affect Mercury's orbit as well. So due to that, there is some precession of the orbit. But even taking those corrections into account, there was still some amount in the precession left unaccounted for.
Okay, I see.
And if you compute the actual contribution from general relativity, it exactly contributes with that amount of precision.
Okay.
I mean, just to say something about that, is that if you look at kind of the low gravity limit of GR, you're going to get a small contribution to the effective potential. That's going to make it not Kepler, which is going to give you a contribution here that kind of pushes it like a very tiny amount. So you can basically treat it most in the same way. So the microphone is back now. Okay, so you can almost treat it the same way, but in some limit. Okay, we have 5 minutes. I want to just grab one more example with this before the break. So let's do that. So the example I want to give, well, it's quite kind of a general example. I'm going to assume a central potential that is V over R equal to some constant K divided by another constant alpha, and that alpha is going to be the same alpha that appears in the power of R. So I'm doing this so that the potential will always be attractive. Because if alpha is negative, then you're going to have still something that grows with R. If it's positive, you're still going to have something that grows with R. So this is going to be an attractive potential in all cases. As we can see, if we just take the derivative V prime of R here, it's K R to the alpha minus 1, which is always positive, which means that you have an attractive potential. So the minimum of the effective potential, we can find that. And that's going to be given by, if we just take the derivative and we take the derivative of the angular momentum term as well, we're going to get the effective derivative, and I'm going to evaluate that at R0, which is the minimum of the effective potential that we already discussed. This is where you have this circular orbit. What we're going to get is minus L squared divided by m R0 to the third, and we have plus exactly this that we wrote down before, so K R0 alpha minus 1. And since we had that this R0, the definition of R0 is where we have the minimum, this must be equal to 0. And from this we can solve that R0 is going to be given by L squared divided by mk to the power of 1 over alpha plus 2. So this is the position of the potential, of the effective potential minimum. And what I need to compute this factor is the second derivative of the effective potential at this R0. So I can differentiate again and evaluate at this R0. And if you do the math, what comes out is alpha plus 2 L squared divided by m R0 to the 4. Okay, but this we can insert into this expression that we have here. And what we get from that is that this delta phi that we were discussing, that's alpha plus 2. No, sorry, it's 2 pi. Looking at the wrong place. 2 pi divided by the square root of alpha plus 2. So this means that our orbits are going to close if the square root of alpha plus 2 is an integer. So let's just look at the harmonic potential, which is alpha equal to 2. Well, that means that alpha plus 2 is 4, and that means that delta phi is pi. And that's 2 pi divided by an integer, so it's going to close. So you have essentially half a lap between the consecutive minima of the radius. Whereas for the Kepler potential, you have alpha equal to minus 1, and that gives alpha plus 2 equal to 1, which gives you delta phi equals to 2 pi. So there you have exactly one lap between them. And I mean, as I said, this is to leading order, but you can actually show that this also goes to any order. We will show it for the Kepler potential. For the harmonic potential, it's pretty simple just to solve the problem exactly, because you can treat it as two separate problems in 2 dimensions. So last hour, we discussed the central potential problem. We discussed different kinds of central potentials. So we also interpreted, in the case of the angular momentum, we interpreted as, or we saw that one result of having a central potential was that the area swept per time unit was constant. And that was Kepler's second law. Then we arrived at this precession, and we saw that a priori, at least to the extent that we could see, that for the Kepler problem, orbits closed. You might know that orbits are actually ellipses. So we're actually going to try to see why, and we're going to try to find Kepler's first and third laws as well. So let's start by discussing the shape of the Kepler orbit. So you might be aware that what we should arrive at is an ellipse. So I'm kind of going to use that to arrive at the solution. What we know for the Kepler orbit is that the energy is a constant of motion. So the energy is mr dot squared divided by 2 plus the effective potential, which is L squared divided by 2 mr squared minus k over r. So this is a constant. Now, as we also saw for bound orbits, the energy E is actually smaller than 0, and for the free orbits it's greater than 0. This can be good to keep in mind. So this describes the motion of r as a function of time, but in order to see what the orbit looks like geometrically, we would prefer to describe it in terms of the angle phi. So to find the shape of the orbit, we want to find r as a function of phi rather than r as a function of t. So what we can do is that we do this derivative of r with respect to phi. And a good trick, as we've seen already many times in the course, is the chain rule. So we can use this to write dr dt d phi, right? This is just the chain rule, and so this is r dot divided by phi dot. So the r d phi is r dot divided by phi dot, and I'm going to define this as r prime. So we use a prime for the phi derivative, and we use the dot for the time derivative. So this means, of course, that r prime times phi dot is r dot. This is also the chain rule. I can go the chain rule the other way as well. And so this means that this is actually equal to r prime, and phi dot we can replace by the angular momentum. So that's L divided by r squared. So now I have an expression for r dot in terms of the angular momentum, r dot, and r, that I can take this and I can insert this over here in the expression for the energy. So this will lead us to an expression including r prime and r. And if we rearrange this expression a little bit, I can solve for r prime squared. And that solution is going to take the following form. So it's 2e r to the 4 m divided by L squared minus r squared plus 2k r to the power of 3 m divided by l squared. So this is something that has to be true for the solution. So I have a relationship between r prime and r now. And now we're going to cheat a bit. So we kind of know from what we have heard that this should be an ellipse. So I'm going to look directly at an ellipse and try to see what kind of statements I can make about the ellipse. So if I look at an ellipse with a focus here, and I define this angle phi here, and this distance r, I can write the distance r as a function of phi. And if I do that, I'm going to get the following expression. So r of phi for an ellipse is equal to sum r0 divided by 1 plus epsilon cosine phi. And so this epsilon is called the eccentricity of the ellipse. And r0, if you look at it, is going to be the distance over here. So it's the distance from here to here, because when phi is equal to pi half, then cosine phi is 0, and so you're just left with r0 divided by 1, which is r0. So this distance here is r0. However, I can differentiate this with respect to phi, and then I can rewrite it in terms of r again. So if I do that, what I end up with, well, I differentiate and I square it. And what this is going to leave me with is epsilon squared minus 1 divided by r0 squared times r to the 4th minus r squared plus 2 divided by r0 times r to the 3. So this is going to be true for an ellipse. However, if you take a look at this expression for r prime squared, then you take a look at this expression that we had for the Kepler potential, you will see that we have a minus r squared term in both of them. We have an r to the 4th term in both of them. And we have an r to the cube term in both of them. So this is essentially the same equation. So by identifying now this coefficient with the coefficient of r cubed here, and this coefficient with the coefficients of r to the 4th here, we can identify the coefficients of this ellipse. So this is going to give us that r0, that's L squared divided by Km, and epsilon squared minus 1 over r0 squared, that's going to be 2Em divided by L squared. So that, if you solve for epsilon, that's with epsilon squared is 1 plus 2E_L squared divided by K squared M. And note now that since we had an energy E, which is negative for a bound orbit, this epsilon is going to be smaller than 1 for bound orbits. Which is good, because that means that we have an ellipse and not the hyperbola. For epsilon greater than 0, you see that this denominator is going to have somewhere where it becomes 0. It's going to have some angle where it becomes 0, and the angle where you fly off at, essentially, if you have a free orbit. Yeah, and of course you can insert here. So in particular, if you let this constant of the Kepler potential K be Newton's gravitational constant times m times capital M, what you're going to end up with is an R0 that is L squared divided by G m squared m, and an eccentricity squared, that's 1 plus 2e L squared divided by G squared m3 m squared. So this is what you get for the gravitational Kepler problem. But I mean, the main conclusion here is that the orbits here are ellipses. For e smaller than 0. And that's exactly the statement of Kepler's first law. So that's Kepler's first law. Any questions on that so far?
Yeah, I didn't really understand your reasoning behind the negative energy that you were saying.
Okay, so if we look at this again, if you look at the Kepler potential here and this energy, if you have an energy smaller than 0, then you're going to have 2 classical turning points, which means that you have a bound orbit. If the energy is above 0, then you just have the 1 turning point, and that's a free solution.
Right.
So for bound orbits, the energy has to be smaller than 0.
When you say energy, you mean the potential or just the?
No, I mean the total energy in the effective problem.
Okay.
So I mean, here you can move between those points. If you are at the classical turning points, the kinetic energy is 0, but the energy is always at this level. It's just that the difference here is the kinetic energy.
Okay. But is that minus sign brought upon the energy by the K over R term? Because we say that the energy is some square term plus another square term plus.
No, so I mean
or
the
minus.
energy, yeah, I mean the energy here is this, right?
Yeah.
It's the total energy. So I mean the energy being negative just means that everywhere this term is going to be larger in magnitude than the sum of those 2 terms.
Yeah.
Okay, so that's Kepler's first law. We have Kepler's first, Kepler's second, and Kepler also has a third law that makes a statement about the relation between the orbital period and the semi-major axis. So for an ellipse, the semi-major axis, which we'll call A, that's equal to R0 divided by 1 minus epsilon squared by definition. And it's going to be the distance between the center of the ellipse and the outer. So this distance. We also have the semi-minor axis, which we call B, and that has this relation that B squared is 1 minus epsilon squared times A squared. And that, on the other hand, is this distance, so the distance to the closest point, which means that the area of the ellipse, that's just pi times A times B. This is the area. And if I square the area, I get pi squared A squared B squared. So that's let's see. Exactly. So it's pi squared 1 minus epsilon squared a to the fourth, right? Now, I had this relation for a here, and I have in the denominator I have a 1 minus epsilon squared, and here I have a 1 minus epsilon squared, which means that I can exchange one of the a's for an r0, and r0 is a constant that. So what we're going to have is pi r0 a to the times a cubed. And so this is equal to pi squared L squared divided by km times a cubed. And now I also know that since I sweep a fixed area per time, so from just Kepler's second law, I know that T, which is a divided by a dot, this is the orbital period, because if I take the area and I divide it by how much area you sweep per time, you get the period. This means that if I square this, T squared, that's exactly a squared divided by a dot squared. And a dot I could express in terms of the angular momentum. So if I just do that and I use this expression up here for a squared, what I end up with is 4 pi squared m, divided by k times a cubed. And this is Kepler's third law, which tells us that the period squared is proportional to the cube of the semi-major axis. So this is Kepler's third law. Any questions on that? Okay, so we're going to move away from central motion, essentially, and we're going to look a bit at the three-body problem. Now, you might have heard that the actual three-body problem is not solvable analytically. So what we're going to do is that we're going to go to look at what is called the restricted three-body problem. So there are some assumptions going in then. So we're going to have three bodies, and they're going to have masses, which I'm going to call m1, which is going to be greater than m2, and they are both going to be much greater than m3, so the mass of the third object. For the sake of things, I'm going to use m for m3. And a further assumption is that m1 and m2 are in circular orbit. Around each other, or around the common center of mass. And what we're going to discuss is the motion of the third body in the potential that's created by those two. So if we look at it, we have one body there. Let's take that color for that one. And we have another body here. It's a little bit smaller. And we have a final third body that's moving in this potential created by those two guys. So those two guys are co-orbiting some common center of mass, whereas what we're interested in now is the motion of this third mass in the potential created by m1 and m2. So any questions on the setup? Okay, so what I'm going to do in order to do this is I'm going to look at the rotating coordinate frame. So that means that I'm going to take a coordinate system such that these two bodies, I mean, they rotate around the common center of mass with some angular frequency omega. And I'm going to take my coordinate system so that it rotates together with this rotation. So I'm going to put my x-axis in this direction and my y-axis in that direction, and I'm going to look at it so that these x and y, they also rotate along with this system. Now that is going to give me some additional terms in the Lagrangian. So the effective Lagrangian for this third body is going to be given by, well, m divided by 2, and then x dot squared plus y dot squared. And then we're going to have, but first of all, we're going to have the gravitational potentials of these of m1 and m2, but we're also going to have a couple of terms that result from the coordinate transformation. And the first one is m omega x dot y minus y dot x plus m half omega squared x squared plus y squared, and then minus v r13 minus v r23 or r1 v1 v2. So these are the potentials created by m1 and m2 respectively. r13 is the distance from m1 to the mass, and r23 is the distance from the second mass to this mass that we're looking at. Now, if we look at those two terms, these additional terms that we have, this guy is a Coriolis term. It depends on these derivatives, so it depends on x dot and y dot. Whereas this term is just an effective potential term, and it's the centrifugal term. And if you look at the contribution of the centrifugal term to the effective potential, so the effective potential that I'm going to discuss here is all of these things that only depend on the position. This is minus the effective. So if you look at the centrifugal contribution to that potential, it's just an inverse harmonic potential. So it's actually a force that pushes you out of it pushes you away from this center of mass. So taking this effective potential, this effective Lagrangian, now we can derive the equations of motions. So the equations of motion, that's just taking this Lagrangian, building the action, and doing the Euler Lagrange variation calculus for that. What results from that is that in the x direction we get mx double dot. That's going to be equal to 2m omega y dot minus dx acting on this effective potential. And the similar thing for the y coordinate. So m y double dot is equal to minus 2m omega x dot, because we had the difference in the sign in this Coriolis term, minus dy acting on the effective potential. So if I insert, or sorry, if I just look at this now, and I ask the question, what kind of stationary solutions do I have? So the question is, what kind of stationary solutions exist? So what's a stationary solution? Well, that's a solution that does not depend on time. So that in this coordinate system, I'm going to be at the same x and y value, and it's going to be stationary, and it's going to be a solution. That means that since the x and y coordinate system rotates along with this original system of two bodies, that means just that this third mass is going to be co-rotating along with this system. So that would be a stationary solution in this case. And for a stationary solution, therefore, since x and y don't change, we have x dot and y dot equal to 0. And that, of course, also means that the second derivative of both x and y are equal to 0. So the only thing that's going to be left of those equations of motions, if we assume a stationary solution, is this. So we're going to look for the extrema of the effective potentials. So when does that happen? So the extrema of, well, let's just write VF. That's just taking the gradient of the effective potential equal to 0. And if we do that, we get the following. We get that omega squared x. That's what we get from the centrifugal term. That must be equal to g m1 divided by r13 cubed x minus x1. So x1 being the position of the first mass here. So this being x1 or minus x1 since it's in the negative direction. In the same way, I'm going to define this as x2. And the second term is then g m2 divided by r23 cubed x minus x2. And so just for looking at what these x1 and x2 are, if you compute what they are, x1 is going to be minus mu r0 divided by m1, and x2 is going to be mu r0 divided by m2, and mu here is the is m1 m2 divided by m1 plus m2. So these are the positions of the masses m1 and m2 relative to the center of mass. And you can see that if you add them weighted by the mass, you get 0. So this is the equation that needs to be satisfied in the x direction. We have a similar equation in the y direction. Omega squared y needs to be equal to y times g m1 divided by r13 cube plus g m2 divided by r23 cube. So if we can solve those two equations simultaneously, we're going to know that putting a mass there is going to mean that it can be stationary at that point. And our problem is to find out where those stationary points are. That's going to be able to tell us something qualitatively about this restricted three-body problem. Now, if we focus on the y, what kind of solutions can you see for this equation?
One is y equals 0.
Yeah. So the first obvious solution is y equals to 0. So we're going to split our solutions into two cases. One where y is equal to 0, and I mean the other kind of solution is of course when y is non-zero, and then omega squared must be equal to the coefficient here in front, right? Or after. So for y equal to 0, then we can look at then our solution is on the x-axis, and we can look at that equation again. So we have omega squared times x, which must then be equal to g m1, and then r13 that we had over here is just the absolute value x minus x1. So oops, we have x minus x1 cubed, and then we have x minus x1 here, and the same term then for the second mass, x minus x2 cubed, x minus x2. So I'm not going to solve this analytically. I'm just going to look qualitatively at what kind of solutions or how many solutions we expect for this. So let me draw something like this. So we have here x, and I'm going to draw both this omega term on the left-hand side and the right-hand side. So if we draw the left-hand side here in green, then that's a straight line. It's omega squared times x. So it's going to look something like, that, right? But it's going to go through the origin. So this is omega squared times x. And if we look at the right-hand side now, so let's make that blue, this guy. If we mark now x1 is here, and let's say that x2 is over here. If x is smaller than x1, well, then both terms here are going to be negative. So, and as I approach x1 from the left, I'm going to go to minus infinity. I'm going to have something like that. If I let x go to minus infinity, I'm going to go to 0. If I do if I'm between x1 and x2, then one of the terms is going to be positive and the other is going to be negative. And this means that I'm going to have something that looks like this. And the solution, or this expression, must go to plus infinity as I go closer to x1, and minus infinity as I go closer to x2. And then on the right of x2, I have this kind of solution for the same reasons as I had this kind of solutions down here. And as you can see, this means that we're going to have 3 solutions to this equation. We're going to have one solution here, because I have one function that is strictly decreasing from 0 to minus infinity, and I have one function that is, well, smaller than that's increasing instead. And it's going up like this. So that gives us one solution there. I have in the middle region here, I have one solution, or I have one function which is bounded and monotonously growing. I have another expression that's monotonously decreasing and going from plus infinity to minus infinity. That means that there must be an intersection somewhere, and that intersection is there. And the same thing here, I'm going to have some intersection somewhere like there. So there are 3 solutions to this equation, and I'm going to label them L1, L2, and L3. And these are all stationary points. So for these x values, you have a stationary solution because the y equation is already solved. and those are called Lagrange points. So there are three solutions on the x-axis. We also need to discuss the solutions that are possible off the x-axis. And if we do that, so that's for y not equal to 0, that gives us omega squared equal to gm1 divided by r13 plus gm2 divided by r23 cubed, right? Yes. There are cubes there. Now you can insert this into the first equation. So this is the equation in the y direction. You can insert this into the equation in the x direction. And what you're going to end up with is that R23 is equal to R13. And that's equal, they are both equal to R0, which is the distance between the two, or between the first two masses. So this distance here is R0, or if you will here, this distance here is your R0. So what does that mean? Let's take this picture and see if we can copy the elements that I want to copy from here. Now I'm just going to make a new picture. So we had our two masses. What color did we have? What was that color? Green? I screwed up the colors, but you get the idea. So let's take a smaller one. So the distance between those two is R0. We know that we have our first Lagrange points. We can mark them here as well. It's going to be one Lagrange point there, one Lagrange point there, and one Lagrange point there. Those were L1, L2, and L3 respectively. Those were the solutions on the x-axis. But we also know that we're going to have these solutions. So the distance between M1 and M2 being R0, we also know that the distance of the third mass, so the mass moving in this potential, that needs to be equal to R0, which means that if we also draw the third mass into this, these masses need to form an equilateral triangle. So because this was R23 and this was R13, they are both equal to R0. So we have this equilateral triangle. So this is our fourth Lagrange point. But there is also an additional possibility of making an equilateral triangle, and that's to have this mass on the opposite side. So we have the fifth Lagrange point here. So in general, we have 5 possible stationary solutions for this three-body problem. Any questions?
What is the direction of M? Is it also does it also rotate around?
Yeah. So the point is now that we were looking for stationary solutions. So stationary solutions in this case mean that I have constant fixed x and y values. So this means that these stationary solutions are solutions for which this third mass co-rotates. So it's stationary in the rotating frame, which means that it's going to rotate along with these first two masses.
Okay.
So typically these Lagrange points are used, I mean, in the case of gravity, for example, in the either the Earth-Sun system or the Earth-Moon system, these Lagrange points are typically good for placing satellites because you need very little input in order to keep them stable there. So just to say that, as it turns out, if you look at the corrections to those stable, those stationary orbits, if you look at the orbits around L4 or L5, there can actually be stable orbits there, which is a bit counterintuitive because L4 and L5 are both local maxima of the potential. However, there is this Coriolis term that makes it possible to have stable solutions around those Lagrange points. Whereas L3, L1, and L2, which are all saddle points of the potential, they are actually unstable. So there you will need some extra input to keep a satellite there. But that's an analysis that we're not going to do. Yeah. So that essentially concludes what I was going to say today, and it's 3 minutes too. So if there are any questions, we can take them.
I have one question.
Yeah.
The Coriolis term and the centrifugal term, how did you know that they had to? I mean, if I were to write this solution, I wouldn't know where to, because from Newtonian mechanics we know that they have to be there, but in Lagrange.
Yeah. So what you can do is that you just write down everything first in the non-rotating frame. Mm-hmm. And then you make a switch of coordinates to the rotating coordinates. So what you would do is something as follows. Let's take a new page for that. What you would do is to say that, well, let's take non-rotating coordinates. And let's call them chi and eta instead of x and y. And then you would, in that case, you would write down something like L equal to m over 2 chi dot squared plus eta dot squared minus the potential, which now is going to depend on both on chi, eta, and time. It's going to depend on time because the two masses that we had, they are moving in this coordinate system, right? So that means that we're going to have a time dependence because the position of those masses depend on time. But then we could define our coordinates x as chi cosine omega t plus eta sine omega t, and y is then minus chi sine omega t plus eta cosine omega t. So this is a rotation that depends on time. And if you make this variable transformation and you insert this variable transformation up here, you're going to end up with the Lagrangian that I wrote down.
Right, thank you.
So it's just a variable transformation essentially. And that variable transformation happens to make this potential time independent.